Good morning. This is part 2 of the section 1-4 homework, otherwise known as the longest homework we've had so far. And so I'm going to start where I left off last time with number 21. And in number 21 we're given a graph and an equation. We're supposed to find the error. So let me just move my book over. And so the function is x plus 1 squared. We know that is a parabola. But what they have done is they've graphed the standard size parabola and they've moved it to the right one, and that has an x through it. So that must be because what we learned about horizontal shifts is that here's my h value, and if this is a plus, that means there was actually a minus 1 in the formula. So it's this minus 1, that's really the h value. And so that is going to be, that parabola should have been to the left 1 unit. In number 25, let's see what we're looking at. Compare the graph of the function with the graph of its parent. So in number 25, you could graph these using a graphing calculator or Desmos, or if you know, if you understand this really well, you can just look at the equation and see what the transformation will be. Let's see, is that cubed? Sorry, need to get my glasses on this morning. So we have a cubic function, not that it really matters. What really matters is what is being done to the function. So this minus 4 right here, that's an h value, so it is a horizontal shift, and when we have a minus, that is going to go to the right 4 units. Number 27, you've got y equals x squared minus 2. So you notice this minus 2 is outside of the parentheses, so that is going to be where your k value is. So a k value is a vertical shift, up or down. So, and this time the sign means the direction that it's going, so minus 2 is simply down 2. Number 29, we're actually looking at a picture of a graph. So we can see that number 29 is a line. So the parent function for a line is y equals x. And then we want to look at how has that been shifted. So it looks like the y-intercept is not at 0 anymore. It's at 1, 2, 3. So it went up 3. So there is the correct equation. In number 31, we have a standard opening parabola that doesn't have a vertex at 0, 0 anymore. The vertex is now at -1, 0. And so that just means that the whole thing has been moved down 1. So we know the parent function of a parabola is x squared. And so the vertex is at 0, -1. Wanted to correct that. And so to move down 1, we want to have a minus 1 outside of the parentheses. Our next problem is number 37. And notice I always just make sure that I read the directions with these problems. Sometimes you have to graph them, sometimes you have to give domain and range. So in number 37, compare the graph of the function with the graph of its parent. So what we're given is y equals -x, and that's inside the parentheses squared. But if we were to simplify that algebraically, we would see that we get the same original function. So I could say that it's the same, but if I'm really being specific, it's actually reflected over the y-axis. So, and just to illustrate that, if we have a standard parabola, and you could draw this, but when we have the negative outside of the parentheses, then that's when it would flip over the x-axis and you would see a change. But since this is completely symmetric about the y-axis, when we reflect it over the y-axis, it doesn't actually change. In number 45, our function is a radical 4x. So we see that we have a C factor, or a stretch or compress factor, that is inside the grouping symbol, and it's a 4, which is greater than 1. Okay, and so I have to go back to my notes on this, or really I just turned to the page right before where it talks about non-rigid transformations. I know that because my growth factor is inside the parentheses or inside the grouping symbols, that's going to be something to do with a horizontal transformation. It's either going to be a horizontal shrink or a horizontal stretch. So I could see that the rule is when C is greater than 1 and it's inside the parentheses, that is a horizontal shrink. Number 51, let's see what we've got. So we're into a new section, so let's see what the directions are. Function G is related to one of the 6 parent functions. Identify the parent function, describe the sequence of transformations from F to G. Sketch the graph of G by hand. Use function notation to write G in terms of the parent function F. Okay, so I'm going to be sketching a graph, so let me get some graph paper. And my original function, or my function that I'm given, g of x, is 2 minus x plus 5 squared. And so I'm going to go ahead, and this is one of the 6 parent functions. So when we have x squared, it's a quadratic. So that is my parabola, or my quadratic parent function. Now, you haven't seen something like this where the 2 is out in front and it's being subtracted. So this is not really in standard form. In order for you to see where everything is and what its effect is on the graph, we want to put that in standard form. So we're going to have our a value in the front, which is just this negative sign right here. And then this 2 is actually, it's a positive 2. So the only way I could switch it around is by bringing a plus with it. So now we see that we have our C value, our H value, and our K value. So let me go ahead and I'll sketch the parent function. So that is going to be a parabola. Let me make a nice straight set of axes here. So the standard parabola, I just kind of always plot these same 3 or 4 points. I go 1, 1, and then 2, 4, negative 2, 4. And then if I have room, I'll go 3, 9, and negative 3, 9. And so that way I can get my openings like correct so that it's the standard size parabola. And then let me do my transformation in a different color. So the transformations that are going to be happening, and let's see, describe the sequence of transformations. So I'm not going to graph each one. I'm going to tell what each one does, and then I'm going to do all 3 at once when I do my sketch. So this negative is it's on the outside of the parentheses, so that's going to be a flip over the x-axis. This h right here has a plus with it, so that's going to be left 5, and this positive 2 is going to be up 2. So I can go left 5, 1, 2, 3, 4, 5, up 2, and put a point. So really the only thing you need to transform, if we don't have any stretches or shrinks, for a parabola is that first vertex point, and then you know that the next 2 points are going to be 1 and 1 on either side of it. And then you know you could go 2, 4, 2, 4. So that is going to be sufficient to sketch that parabola. So problem number 55, the directions are the same. So we're going to have our g of x function that's given. In this case, it's 3 times x plus 2 cubed, or sorry, 3 times x minus 2 cubed. So we can identify the parent function. That's going to be our cubic. And so let's go ahead and start by graphing the parent, and then we'll talk about all of the transformations that are going to take place. So on my graph paper, I don't have a coordinate plane already driven. I think what I'm going to do, and I should have done this already, is just make a photocopy of a bunch of coordinate planes for you guys and distribute those. That's probably the easiest, or you can use your own graph paper. So the original cubic function is 0, 0, 1 cubed is 1, 2 cubed is 8. So 1, 2, 3, 4, 5, 6, 7, 8. And then on the negative side, we just have to go 1, 2, 3, 4, 5, 6, 7, 8. We go to the positive x, or the positive y's over here, and the negative x's get negative y's over here. Okay, so what is going to be happening in my transformed function? It looks like I've got some sort of a stretch or a compress, and it's outside the parentheses, and then here I've got an h value that's inside the parentheses. So let me start with that one, a minus 2. We know the minus, we are going to go to the right 2, and then this c value, again, this is one that we're going to have to memorize, but with that c being on the outside of the parentheses, that is going to be a vertical something or another, and so we want to see, is it going to be a stretch or is it going to be a shrink? So when c is greater than 1, it's going to be a vertical stretch. So let's go to the right 2, 1, 2, and see what happens. So now my vertex is at 2, 0, and if I go 1 over from there, that's going to be where x equals 3, and then also if x equals 1. So if I'm not sure, this vertical stretch, sometimes it can throw me off with my graphing. So if I am not sure how to graph that, well, number one, you guys probably have a graphing calculator or a graphing utility. So if you're on the ACT or something where you're allowed to use your calculator, you can just plug it in. But I'm going to do this by hand. So if I'm stuck, I can do 3 times 1 minus 2 cubed, and I can also do 3 times 3 minus 2 cubed. So the 1 minus 2, that's going to be on the left side, so I'm predicting it's going to go in a downward direction. So that's going to be 3 times, well, let me write it out here, 3 times negative 1 cubed. So that's a negative 3. 1, 2, 3. So you see how the first point on the original parent was at negative 1, negative 1. So now we're negative 1 over from the vertex, but we're going down 3. So it's vertically stretching it. It's 3 times as long. So I go 1 to the right up here. Well, let me just plug it in to verify. So 3 minus 2 is 1, 3 times 1 cubed, and we're just going to go up 3. So all the shifts are proportional, and so then the next one is literally going to be, if it's 3 times as big, it'd be 3 times 8, so it'll be off the chart. So this gets really steep really, really fast. Okay, so number next, what's next? 59. So let's see what 59 is. Same sort of problem where we have to look at the original parent and then tell what it's going to do. So number 59, this is our first rational function. So g of x, how do I know it's a rational function? 1 over x plus 8 minus 9. So our original parent function is going to be the rational function of 1 over x. So let's go ahead and graph the parent and then we'll see what happens. So this is one of those where, you know, we haven't seen a rational function yet in this class. So unless you've just opened your book and been studying your parent functions, which I haven't even asked you to do that, and honestly, we're going to have a whole bunch more focus on rational functions. So we don't need to know this by heart. So what I'm going to do is turn to the guide in the back with all of my parent functions. And so I see that I've got asymptotes with rational functions. So my asymptotes are my axes, and that means the graph is never actually going to touch because we can never have a 0 here. So probably that is part of the domain or whatever, because you can't have x equals 0. But so if we plug in a 1, our point is 1, 1. And then if we plug in a 2, then we get to a half. And then here, between 0 and 1, there's a million fractions. So like if I plugged in a 2, a half, 1 over a half is 2. 1 over a third is 3. So this thing it's going to get closer and closer and closer to the axis but never actually touch it, and the same is going to happen over here. And so the same thing happens on this side. So this is what the rational function looks like. Rational functions always have an asymptote. So now we know what our original function looks like. Now we need to see, it looks like we've got an h value and a k value. So a plus 8 is going to go left 8, and a minus 9 is going to go down 9. And so the way we shift a rational function is we actually shift the asymptotes. So, and then the function is not being stretched or compressed, so I'm just going to copy it. So hopefully I have got enough blocks on my grid here to go left 8, 1, 2, 4, 5, 6, 7, 8. So I'm going to draw an asymptote over here at -8. So I probably should have drawn my original axes a little bit differently. But so I'm going to draw my asymptote as a dashed line, and then I'm going to go down 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So now I'm just sketching these asymptotes, and I'm going to draw the graph as though those were the x and y axes. So there was no negative sign, nothing flipped. So I'm just going to go up 1 over 1 to that 1, 1 point, and then I'm going to sketch my curve. I'm going to do the same down here. So this asymptote keeps going. So that's what happens with that transformation. Then number 61, same section. This time we've got a absolute value function that is stretched, compressed, you name it. So my g of x, -2 times the absolute value of x minus 1 minus 4. Then, so I can recognize that as the absolute value function. So when I draw that one, Okay, so my original parent function is the absolute value graph, so it has a slope of 1, 1. That would probably help if you could see it. And then let me draw it on this side too. Okay, so we've got a C value, an H value, and a K value. So let me do H and K first. Those are the easiest. So minus 1 is going to be right 1. Minus 4 is going to be down 4. Then out here I've got a negative on the outside of the parentheses, so that is going to be a flip over the X. And then this 2 on the outside of the parentheses is going to be a vertical shift, and it's greater than 1, so it's going to be a vertical stretch. So let me just write that. Vertical stretch. Okay, so let's move our vertex first. So right 1 and down 4 is going to go right 1, down 4. And then I can't just draw the original parent function because I have this vertical stretch. So I know my graph is going to be going in the downward direction. So instead of going over 1 and down 1, I'm going to have to go over 1 and down double in the vertical direction. So instead of going over 1 and down 1 each time, I've got to go down 2. So what I find ironic is it's a vertical stretch, so every time you go down, you go more. But it's weird to me that a stretch is actually skinnier than the original graph. So that's where naming what it is going to be a little bit challenging. Or that's why I always have to look it up, because that plays tricks on my mind where it's skinnier, but it's called a stretch. So you just have to kind of memorize those. All right, last one, number 69, and that has a star by it, and it says explain. So all these assignments I get from the department, the math department here at Hardin Valley. So I am not setting the assignments. So let's see what we want to get out of number 69. So use the fact that the graph of y equals f of x has x-intercepts at 2 and negative 3 to find the x-intercepts of the given graph. So let's see. Let me move this over here. Okay, so if I have some kind of a graph that has x-intercepts at 2 and negative 3, what, and then f of negative x, I want to be able to know where are the x-intercepts for that one. So first thing we have to do is figure out what kind of a transformation is that. So with the negative inside the parentheses, that means our C value is inside the parentheses. That's some kind of a horizontal shrink, right? And there's not a coefficient, so that means it's a negative 1. So a horizontal shrink is a flip of negative 1 is a flip over which axis? Horizontal. We're actually flipping over the y-axis. So when we have these two x-intercepts, if we were to flip that over the y-axis, Well, I'd probably just, if I put this point over on the other side, that would be at positive 3. And if I flip this one and put it on the other side, that would be at negative 2. So I don't know how you would verify that. I'm reading the directions for the wrong section. Number 61. No, 69. I think we've answered it. Find the x-intercepts. If not possible, state the reason. We don't have to worry about that. And that concludes your homework for 1-4.